So welcome back. From today onwards, a few lectures, we are going to talk about the materials, and particularly we are going to deal in the mechanical properties of solids and fluids. One of the major things about these mechanical properties of solids is elasticity. So we'll talk about elasticity, and elasticity is present in all forms of matter, the solids and the fluids which comprise liquids and gases. As I told you that these forms of the same matter, the solid form, the liquid form and the gaseous form, this is a matter of the order of arrangement of order. Solids are the most ordered system. The liquids follow that order, level of order, and the gases are the most disordered systems. The matter is comprises of atoms or molecules, whatever, and the intermolecular distances are maximum in the case of gases. Then that distance closes and there is more neighborhood in the case of liquids, and these liquids, they make solids in the crystalline form and also in the amorphous form. So that depends how the solids crystallize and how they remain amorphous. Okay. So these are the various forms of matter. Actually, solids, for example, they are the colonies of atoms and molecules arranged in a certain fashion. Every molecule is surrounded by other molecules. We have some nearest neighbors, next to nearest neighbors, next to the nearest neighbors, and every nearest neighbor is also having its own nearest neighbor, set of nearest neighbors. They interact with each other, they have a binding with each other, and they have the kind of a binding energy which is obtained in the case of solids, but less so in the case of liquids and gases. Now, all along in the previous lectures, we have been talking about rigid bodies, and we have considered that these rigid bodies are near ideal rigid bodies. The rigid bodies are solid bodies that cannot be deformed. That cannot be deformed. And if they are deformed, we understood about the rigid bodies that they are not rigid. Okay? If deformed. So, in those discussions, we didn't think that even these solids which you're talking about, they can be deformed. Okay. Practically, that is why I say that deformation is a rule rather than exception. Okay? Deformation is a rule. Now, for deformation, bear in mind that a pair of equal and opposite forces is a must. Because else there will not be an equilibrium, there will not be a possibility of a discussion as to, however, of the pair of the forces, we often choose one force and develop our theory on that. So now there are materials in which there is a plastic deformation. Elastic deformation. Elastic deformation is such that if the deforming forces are withdrawn or they are removed, then what happens is that removing or withdrawing the deforming forces, what happens? That the body under deformation returns to its original shape, size, etc. Okay. This phenomenon in which after the deformation has taken place, after the forces have been applied, after an experiment has been done or whatever, then they return back to the original shape and size. Of course, in elastic deformation, we talk about an elastic limit. And the deformation, you see in the case of metals and alloys and many other things, is not very high, maybe 1% or 2%, and beyond that its behavior will become different. We'll talk about that behavior shortly. Anyway, of course, substances like rubber, etc., the deformation is much more, even sometimes of the same size as the original length, etc., and such materials, such things are known as elastomers. We'll talk about that later. Now, there is another kind of deformation, and that is called plastic deformation. Plastic deformation. In plastic deformation, once the deformation takes place and we withdraw or remove the forces that have deformed the body in a new shape, etc., if we withdraw that, then there is no return to the original shape. Okay? Such bodies are called plastic bodies, and the deformation is called plastic deformation. Now, to discuss the elastic behavior of solids, we talk in terms of spring ball model. In the spring ball model, I'm just taking it as a spring, as a representative of the spring. Here there is one ball and it's another ball, and in between there is a spring. So what will happen, that there will be some kind of vibration that will take place, and the neighborhood, and there are so many springs, you can look, I can't make that picture for you, but all books, they do show the picture of the spring ball model, where there are vibrations and the things are restored, and the elastic behavior of the solids can be explained in terms of that spring ball model. Now, there are two things. If we apply the pair of forces, what results is a stress, deforming stress and restoring stress. The stress I will define later on, and then there is a strain. When the de-shaping takes place and deformation takes place, then there is something called a strain. And stress and strain have to be studied, have to be defined properly. For example, whatever kind of a stress is there, we define it as one of the forces which is applied out of the pair of the forces divided by the area which responds to that pair of forces So stress is equal to the force divided by area, and force divided by area is also known as the pressure. So this is newtons and this is meter square. So the unit that we get in the SI system, in the system international, in the MKS system is called Newton per meter square or Pascal, which is the favorite unit of pressure. Dimensional analysis if we do, so I always tell you that, remember this, Mr. Force. Mr. Force is very friendly to us, and it is MLT minus 2. LT minus 2 for acceleration, M for the mass. MLT minus 2 I remember, I'll divide it by L square, and then quickly, in a split of a second, I'll tell that ML minus 1 T minus 2 is the dimensional equation that we arrive at. So we were talking about the stress and strain. Now I'm just introducing to you various kinds of situations in which we can talk about the stress and strain. In the first case, I talk about longitudinal stress and longitudinal strain. So what is happening is that I have certain wire or cylinder of a certain area of cross section. A is the area of cross section here. So the stress will be equal to, now if I apply a pair of forces, F and F here, then what we find is that there is an elongation, and this elongation has been shown to be very large as compared to this thing. It's not so, it's never more than, in the case of most of the solids and alloys, it is about 1 to 2%. So within the elastic limit, what happens is that this stress, in the red color I have shown it to be of length L, and later on it becomes equal to L plus delta L. I am taking advantage of this. Again I will, so this longitudinal stress is called tensile stress. Okay, so the same like that, F divided by the area which we consider, because the deformation in the length has been such that almost we can say that the area of cross section remains the same. So it is F upon A, that will be the stress, a stress which we call longitudinal stress, and in this case because the length is increasing, we often call it tensile stress. Okay, F upon A. In the second case, I have shown that the original length is L and there are no forces. Okay, the original force in the green color is L, and when I apply a pair of forces compressing it, of course all the two forces have to be equal and opposite, so that its position is restored, retained, and it does not go away with an acceleration. So I show that first of all the length is L, then the length becomes equal to L plus delta L dash, and this delta L dash is less than 0, so that actually the length becomes smaller. So this stress we call compressive stress. Okay, the compressive stress belongs to this. Okay, And then in both the cases, we find that there is a longitudinal strain, and this strain is delta L upon L. Having the same dimensions, length upon length, this is a dimensionless quantity. In fact, all such quantities are dimensionless. Okay, like in volume strain I'm writing, etc., etc. So remember, there are external deforming forces, and then there are internal restoring forces. They come into play. So therefore, this phenomenon over here is the tensile stress and the longitudinal strain thing. In the second kind of a deformation, what happens is, I've taken a cylinder over here and I'm applying a force in this direction, one face of it. Okay, so what happens? That there is a deformation, there is a lateral deformation, and of course this is held in this position. The area is there, the force divided by the area will give us the shearing stress. Actually it is a kind of shearing stress, and there is a deviation over here, and that means there is an angle theta that this length makes with the original direction, and there is a displacement at the top which is equal to delta x, okay, which is shearing. So what we say, we call this stress which is applied because of the pair of the forces at the bottom and at the top. Okay, it's like this, the forces is going like this, other force is coming like this, and in between the cylinder goes some deformation, some kind of a stress is developed, and we call this stress also, shearing stress is called tangential stress, okay, which is again F upon A like before, and the shearing strain is this delta x divided by L, and naturally the two of them are the same dimensions, so length divided by length gives us a number, and this number turns out to be equal to tan theta. Okay, so this tan theta shows the strain, the shearing strain which appears. In the third one, I've just shown you, it's like a book is there, and the book is on a solid platform, and what I am doing is I am applying a shearing force which deforms the book slightly, okay, and this is the condition which is akin to this condition. So these pictures, these drawings, schematic drawings, they show as to what is the situation for the shearing stress and the resulting strain, which we call the shearing strain. Now there is third situation. For example, I have a body, a solid body of any shape, and this is taken to a depth in a tank, in a river, or maybe in a sea. What happens is that on this body I have forces which are perpendicular to the body, which are equal in value, like this, okay, from all sides on the body. I'm not showing it. From all sides of the body there are forces that press it, and because this is the kind of thing which often happens in water bodies, so therefore this stress is called the hydraulic stress. And this hydraulic stress again is the same as the pressure. The pressure from all sides, equal pressure is there, so the body gets D-shaped. And of course, the shape of the body remains the same, but it is under hydraulic stress, hydraulic pressure. Now remove it. If we bring back the body up on the surface of that water body, then it returns to its original position. Okay, and there has been a volume strain, which is the volume of the body originally minus the volume of the body finally under the stress, and that is delta V upon V, and again you can see that it is a dimensionless quantity. So these are the kinds of strains that we have. Now, in all these cases, in the case of tensile, or in the case of shearing, or in the case of this bulk thing where there is hydraulic pressure, we have certain constants which we will discuss shortly. But the thing is, you apply the forces so that the body becomes tense. The body becomes tense. That means because of the restoring forces within the body, from molecule to molecule, from neighbor to neighbor, there are disturbances, and those disturbances, like in the motor, if you want to take it apart, then it will try the restoring force, set of forces will try to bring it back, and if you remove that, we restore that. And in between, when the forces are applied and there is a deformation, and when the forces are removed, there is a restoration and original things are obtained. In the case of the elastic limit not being exceeded, then that is called the tension. The state of tension exists inside. Okay, we'll talk more about it. So let us deal further with the case of elasticity concerning wire and test cylinder. So we are doing the tensile thing. Okay, so I have got this wire with an area of cross section equal to A and length L, and of course when the two forces are applied equal and opposite to each other, there is tension in the system and the length increases to L plus delta L. So this is one way of increasing the length. Can you think of another way? There is another way, and that we will deal later on, that if we heat, then also the molecules get separated and the length of the system may increase, and that depends, the increase depends upon the change in temperature, etc. We will deal that later on. Now in this system we have the stress, which is the restoring force per unit area, which we take on the y-axis. Stress is shown by the Greek letter sigma, and on the x-axis we take the strain, and we find that stress is proportional to strain. Of course, within the elastic limit, whatever is the limit, within our limitations, we find the result is that the stress is proportional to strain. So it's a system, and in this system there are two variables. One is the stress and the other is strain, and stress is proportional to strain, just like y is proportional to x, y is equal to kx. Okay, So similarly, this stress will be equal to K multiplied by the strain. This is the constant of the proportionality of the defined system, and which does not depend upon the strain, does not depend upon the strain. At all points, the slope of the stress-strain curve is constant. So sigma upon epsilon. Epsilon is the strain. Okay. So we find that the slope is a constant is equal to sigma upon epsilon. It can be also said to be delta sigma upon delta epsilon, keeping with our traditions that we have been doing in the y is proportional to the x system. Okay. So stress is proportional to strain is equal to K times strain, and this K is the modulus of elasticity. Now the stress is F upon A, the force per unit area, and the strain is delta L upon L. So I get F upon A is equal to Y delta L upon L, where Y is called the Young's modulus of elasticity for the tensile case. So my Y turns out to be equal to, I can write an equation that my Y, the Young's modulus, is equal to FL F into capital L upon A into delta L. Okay. And interestingly, because strain is in all cases is dimensionless, so the modulus of elasticity, whatever Young's modulus or bulk modulus or the other modulus, shear modulus, they all will have the dimensions of stress. Okay. Now let us see and look at a situation as to what happens if the pair of forces that we are applying is increased and increased and increased and increased. Okay. So there is a stress-strain curve which turns out over here to be initially for about a couple of percent of the length when the strain is not too much. The stress is proportional to strain and we get a straight line. We get a straight line from point O to point A. Okay. Thereafter, the linear dependence changes and there is a kind of a non-linear dependence, and we reach a point B. Okay. We reach a point B which we call the yield point. There is a kind of a plastic deformation which creeps into the system. And if from this sigma y, this value, we change it little bit, then ultimately we reach the position D, the maximum position which we call D, which we call the tensile strength point. Tensile strength point. And after that, if we want to apply the stress, then of course the stress decreases, but still the curve goes ahead, and this point E is called the fracture point. At the fracture point, the wire or the cylinder will give way. So it is fractured. So naturally, what we are doing is we are just studying the case of this tensile system, and here between the point B and the point D, if we take a point, for example C, then what happens? Up to the point C, when we reach, what we do is that we start decreasing the value of the stress. As the value of stress is decreased, so this path is not retraced back. This path is not there. It doesn't take this path, but instead it comes, and there is a permanent deformation over here, and this deformation has been shown in this curve. The curve is not is roughly drawn by me. I'm not good at that. So there is a plasticity which comes into the system. That means that it doesn't come back to the position L, but instead it has an L plus something, but this something is, for example, has been shown to be less than 1% departure from the original length. Okay. This sigma y corresponds to what we call the yield strength. Yield strength. It corresponds to the point B, which is the yield point. The maximum that we can apply to the system before it gives in, is called sigma u, which is ultimate tensile strength. U for ultimate. Okay. And after that, of course, at the point E, it can be here, it can be here somewhere. The system fractures, breaks, and of course, between this point and this point, there is a kind of, I can have the return to a value close to the original value, but is still distorted from the original value, and we get, this is how materials they behave. Of course, we'll see that materials like India rubber and even the aorta, they behave in such a way, the muscles of the heart, and I'll talk to you about that, how the muscles of the heart, they function, and what is the physics that is involved in that, and we elastomers that we call them, these materials, and we'll talk about that plus many other things about other moduli, but today we have just done one modulus, Young's modulus of elasticity, and we have seen that the mere force we are applying to change the length of the wire oblique the cylinder, or we are applying to compress that wire or cylinder just to arrive at the Young's modulus of elasticity, which is a signature for different metals, alloys and materials. So about solids, this is an important aspect, and similarly we get the modulus of elasticity for the what we call the modulus of rigidity and shear modulus, etc., etc. So I have enjoyed, and I hope you have enjoyed too. Do make this for yourself or copy it from the books, which give a nice drawing, and do understand these points, how they are there. Okay, so for today we close here, and when I close, then I point towards this point, and I have received some queries, some questions, and I've been I studied those points and I answered to the people who asked those questions. So hope that you enjoyed, and keep on enjoying that. Thank you very much.